In the last lesson, I mentioned that formal charge was going to help us to distinguish between a structure that's just valid and a structure that's actually the best structure for a particular formula. So formal charge can be used to help us figure out if something is likely to be stable or not, the way we have the electrons arranged. So essentially, what it comes down to is that molecules or a structure is likely to be most stable, and as with most things, there are exceptions, but the structure is likely to be most stable. There we go. When as many formal charges as possible are as close to zero as possible. So if you have multiple options for structures that you can draw, generally the best one is going to be the one that minimizes formal charge. So you will frequently find that this is one of the major reasons why expanded octets tend to happen. That creating an expanded octet minimizes the formal charge, and that is actually preferable, that it is more stable to minimize the formal charge than it is to just follow the octet rule. Things that are capable of having expanded octets don't really mind. It's not destabilizing, particularly for them to have more than 8 valence electrons accessible to them. So many electrons will, or many compounds, sorry, will create an expanded octet, or sometimes an incomplete octet, on the central atom in order to minimize formal charge. Sometimes you can't get rid of them all. There are absolutely instances where you need non-zero formal charges. If your formula is charged, you need some non-zero formal charges in there. And even for neutrally charged molecules, sometimes it's just not possible to get rid of them all, and that's fine. But you do the best that you can. So usually we want as many as close to zero as possible. And in fact, formal charges greater than plus or minus 1 are extremely rare in stable compounds. So plus and minus 1, super common, you find them all the time. If you see a plus or minus 2 or a plus or minus 3, that should be a pretty big red flag to you that there is probably a better structure that you can draw. One other thing to be aware of that doesn't come up super often, but if you have a choice about where to put a formal charge, so like I need a negative 1 somewhere, if there are options for where it can go, came out ugly, let's try that again, it's a little better. So if you can say either place your charge on an oxygen or a sulfur, what you want to look at is the electronegativity of that element to determine where it's going to be more stable. So essentially negative formal charges are more stable on more electronegative elements. Those elements are better able to accommodate that extra electron density because they want to attract electrons towards them anyways. So negative formal charges mean there are extra electrons around, so they're going to be more stable on something that is highly electronegative. And positive formal charges tend to be more stable on low electronegativity elements. But the most important thing is usually to just minimize it, make them as small as possible. So in the previous lesson, come back, oh no, shifted things. There we go. In the previous lesson, we looked at these two examples. We drew structures based on the rules that we've been following, came up with things that follow the octet rule. So they are valid structures, but they're actually not the best structure in either case. So both of these have more formal charges than is necessary in order to be as stable as possible. So let's look at SOCl2 first. Everything here follows the octet rule, but we end up with this -1 formal charge on the oxygen and this +1 formal charge on the sulfur. So what we can do to actually make this more stable is create a double bond, is move some electrons away from this negative formal charge, take one of these lone pairs, and make it into a double bond instead. So what we end up with is everything else stays the same, but we have a double bond here, and this oxygen will only have 2 lone pairs. And now we haven't changed anything about the electron arrangement around our chlorines, so those still have a formal charge of 0. Our sulfur now has 1, 2, 3, 4, 5, 6 electrons, which is the same as its typical number of valence electrons, so that brings its formal charge to 0. And the oxygen has 1, 2, 3, 4, 5, 6, which is also the same as its typical number of valence electrons, so its formal charge is 0 as well. So in this structure, all of our formal charges are equal to 0, so this is likely to be the more stable of these two structures. And what this molecule actually looks like is that it does have a double bond there. So sulfur creates an expanded octet. If we're thinking in terms of filling valence shells, this sulfur has 2, 4, 6, 8, 10 electrons. It has an expanded octet, but sulfur is capable of doing that, so that is fine. By minimizing the formal charge, we have made this structure more stable. See if you can try to draw the most stable, or at least a more stable, structure for the sulfate ion, for SO4 2-, using similar principles of creating multiple bonds in order to bring our formal charges down. So pause here and give that a try on your own. So we're going to take a similar approach here, that we can, oops, want the paler color, move some electrons away from a place that has a negative formal charge towards a place that has a positive formal charge. So we're taking a pair of non-bonding electrons and making them into bonding electrons. So instead of having full ownership of both of these, this oxygen is only going to have ownership of one of them, and then sulfur kind of gets ownership of the other one. So if we move one pair, let's make that smaller, one pair of electrons, we will get a double bond from that top oxygen. So we have not changed anything about the electron arrangement of the left, bottom, and right oxygen atoms, so those formal charges stay the same. For our sulfur, we now have 1, 2, 3, 4, 5, so that gets us a formal charge of +1. And then our oxygen has 1, 2, 3, 4, 5, 6, which is the same as its typical valence, so that one becomes 0. So we've made some improvements. We've gotten rid of one of our formal charges entirely, and we have brought the +2 down to +1. So this is a more stable structure than the first one that we drew, but it's still not actually the best. We can do the same thing again from any one of our other oxygens. Doesn't matter which one, they're all equivalent, so you can have your double bonds in any position and it's going to be the same. We don't want to mess with this one again because we've already got its formal charge to 0, and if we change it again, it's going to become not 0. So if we took another lone pair from here, this formal charge would be at +1, which is not going in the direction we want. We always want to move towards 0. So if we take a pair off of something that is negatively charged and move it towards our positive charge, that is going to be helping us. Moving electrons away from that negative formal charge is going to help bring it towards 0. So I still have not changed the left and right oxygens at all. I now have double bonds to 2 of my 4, the top and the bottom as I've drawn it. Again, if you have different ones, that's fine. This top oxygen is the same electron arrangement as it was in our previous structure, so that's still going to have a formal charge of 0. You will notice that the top oxygen and the bottom oxygen have the same electron arrangement now. They both have 2 lone pairs plus 2 bonds for a total of 6 electrons in the formal charge counting sense. So the bottom one now also has a formal charge of 0. And the sulfur is involved in 2 double bonds and 2 single bonds for a total of 6 electrons, which is the same as its typical valence. So that also has a formal charge of 0. So we still have these 2 -1s on these oxygens, but we have an overall charge of -2, so we need that. Remember that our formal charges need to add to the charge on the species, so we need to have a total of -2, and having 2 -1s is the best way to do that. So this is the best structure that we can draw for sulfate. Again, with any arrangement of double and single bonds is fine, but 2 doubles and 2 singles is where you want to end up for this one because it is the lowest possible arrangement of formal charges. So if you play around with this more, you can come up with other arrangements that have like other charges on the sulfur. There are loads of structures that you can draw for this ion, but all of them end up worse than this one or some version of this. So one last brief thing to note is that all of these different versions of the same structure that we're drawing are what we call resonance structures. So anytime you can draw 2 different structures for the same compound and they're both valid, this only applies to things that follow the rules that they need to follow. So resonance structures are just different arrangements of electrons on the same arrangement of atoms. So for these structures, we have, sulfur atom in the middle, 4 oxygens around it. We have the same arrangement of atoms in all of these structures. The only difference is where we're putting the electrons, and we call those resonance structures.